Which one should they launch first?
100.
Kevin says 100.
That would be Derek. Kevin says 500.
My goodness, I do that every day.
Yeah.
Derek says 100. Derek, why 100?
So it can get out of the way faster.
So it can get out of the way faster. Okay. Kevin, which one do you think?
500.
500. Why 500?
Because it's going to move faster to stay in the same area.
It's going to move faster to stay in the same...
Radius.
The radius?
Same spot.
Okay.
Let's take the 500.
You said the 500 plot 100 over?
Yes.
Okay. So, anyone else? Who says 100? Gulnas.
I also think that it moves fast because it has less mass.
Okay, so Gulnas says the 100 will move faster because it has less mass. Okay. Anyone agree with Gulnas? Okay, a couple of you. Okay. Who agrees with Kevin about the 500? Okay, Kim, why do you say 500?
It might have a bigger force.
It might have a bigger force. Okay, so not it might have a bigger force. It will have a bigger force. F equals GMM over R squared, right?
What?
F equals GMM over R squared, right?
Okay.
Big G, big M, those don't change. R's not changing. Nothing that's changing is the little m, right? So 500 kilograms will have a bigger little m, if you can follow that, all right? So if there's a bigger little m, that means more force, doesn't it? Supposedly. So 100 will have a faster velocity because it's lighter. 500 will have a bigger force, so it'll move faster. Those sound like our two arguments, don't they? Anyone else have something to add?
Send them off at the same time. Just let them crash.
Set them off at the same time, let them crash.
One has more.
So then we'll have one non-functioning satellite of 600 kilograms.
Well, if you launch one
Sounds like a tremendous waste of money. Please don't go into Verizon, okay? I like my cell phone working. All right. Anyone else? That's when I switch. Once Sergio gets the job of Verizon, I'm switching coverage. Anyone else?
Does not matter.
What? Moses, what do you say?
It doesn't matter.
It does not matter. Why doesn't it matter, Moses?
Because the Earth is the big mass.
The Earth is the big mass.
They're both small.
They are both small, but in the GMM equation, F equals GMM over R squared equation, right? Newton's law of universal gravitation. These masses play a role, don't they? So, does it matter? Not really. So, let's see. Richard, want to hit the lights for me real quick? Thank you, Richard. Julian, want to jump up and turn off the projector? Thank you. All right, so consider this. Here's what?
I'm guessing that's the Earth wall.
See, man, you guys are awesome at Pictionary. You guys need to come to my house next time I play Pictionary.
I don't know what
Okay, so what is that?
Earth.
Earth. Okay,
What is
so
It's like a broken.
thank you guys. Two satellites,
Marvel.
right? Now, I'm not giving you a direction yet, so that way you don't know which one got launched first. And how far are they away from the Earth?
100.
100 what?
So
100 kilometers. Okay. Do you guys think this is to scale?
No.
No, it's not to scale. Because if this is to scale, it means the Earth has a diameter of about 300 kilometers. Okay. So this is not to scale. So they are both 100 kilometers away from the Earth. And the question is, which one should she launch first? Because we're worried what's going to happen. It's going to collide, right?
It doesn't matter.
Now, as these satellites go around the Earth, and no, I'm not indicating which one should go first by my circle where I started. Okay? As the satellites go around the Earth, what type of motion are they going through? What was that again? Centripetal motion. Right? And here's the reason why I linked these two together. Centripetal motion, motion in a circle. Okay? Based on motion in a circle, what do we know about acceleration and velocity? AC, A centripetal equals what?
Velocity squared over 3.
Good. Velocity squared over the radius. Right? Correct? Okay. Now, I don't know what you said.
Oh, no.
Now, what was I going to say? Okay. For these satellites, do we have an equation for their acceleration? Because what's causing the centripetal motion? What force causes centripetal motion? What is it, Lynn? Gravity. Right? Both these satellites experience gravity towards the Earth, don't they? So gravity is what's causing this centripetal acceleration, right? What we just learned the equation for gravity, didn't we? Because we know it's not 9.8. They're not on the surface, are they? It's something else. How do I find that something else? Moses, a little louder.
A equals GM divided by R.
Okay, so A equals GM divided by R squared. And what M is this? Planet. So this is the Earth or any other planet, right? Not the satellite. So now when I combine these two equations, hopefully you quickly come to a conclusion when you see these equations both lack what? What's not in this equation? What'd you say, John? Little m. Little m is nowhere to be found, right? So does it matter which one we launch first? No. The mass of the satellite does not affect its velocity, right? Because velocity is the thing that's going to cause it to collide, isn't it? Right? If one's moving faster than the other one, then we're going to have an issue, right? But based on this equation, based on what we have right here, and I can simplify this down a little bit, I have an r on both sides. What do I do with one of my r's? Cancel, so I'll cancel this one and drop this squared. Does that make sense? Okay. So now I have an equation where I have GM, not General Motors, or the guy in charge of the Lions, either one. Okay. Now what do I do? How do I solve? Square root. We gotta do something radical, right? You get the joke, thank you. That's called a radical. We got to do something. Alright. So we have the square root GM over R equals velocity. And that is our equation for the velocity of the satellite. So what we learned here is there is no little m like John said. Since there's no little m, the only thing that affects the velocity of these satellites is what?
The planet.
The big M. And the radius. The only thing that affects the velocity is the big M and the radius. Now this works just like centripetal acceleration did. And centripetal force did. Okay. What happens to velocity if radius goes up?
It goes lower.
It goes lower, right? What happens to velocity if mass goes up?
It goes higher.
Goes higher. Right? It's the same thing we had when we had centripetal force. So is there any questions about that equation? Any questions about that equation? Okay. We could also start with F equals GMM over R squared, and then use F equals MV squared over R, cancel the M's and get the same result. So, I think that flows a little easier. Are there any questions about that? Kim?
So for example, the mass doesn't matter.
The mass does not matter. Because there's nowhere to put mass in this equation. The only mass in this equation is which mass? The planet. Okay? So it does not matter how big they are. They will travel at the same velocity. So the only issue the engineer has is making sure they don't launch the 500 kilogram satellite when the 100 kilogram satellite's in the way. Right? So we're going to want to make sure that it's got a good enough head start. Okay. So if we're going this way around the circle, that would probably work. Right? If we're going the other way, that'd be a little nervous for me. That means I'd be launching the 500 kilogram one up into the... I guess it depends which one you launch first. But it doesn't matter which one you launch first. Does that make sense? Julian, headphones off. Alright, I want you guys to figure out the velocity of the satellites.
Thank you.
Okay? I gave you a little help. The radius of the Earth is. No, thank you. Page 173, guys. Guys and gals. That sounds kind of weird. Okay. The radius of the Earth is 6.38 times 10 to the 6th meters. The mass of the Earth is 5.97 times 10 to the 24th kilograms. So, can you guys find the velocity? Sergio, I'm not asking do you want to find the velocity, I'm saying find the velocity. So, your opinion on that doesn't really matter. Yeah, I appreciate your politeness. Hey, Kevin. This is the only class that matters. As long as you pass this one, I'm happy.
Oh, you're happy.
Now, one thing you have to be aware, guys, is do not write the r squared. Okay? Because you're so used to putting r squared on the bottom, you got to make sure when you do this one, you don't put the r squared on the bottom. Okay? So let's plug in what we know. We're on time. So big G is 6.67 times 10 to the negative 11. The mass of the Earth is 5.97 times 10 to the 24th. The radius was 100 kilometers, right? Right? So we have to add 1 times 10 to the third to this number, don't we? Right? Or sorry, we add 100 times 10 to the third to this number, don't we? So our radius is 6.38 times 10 to the 6th plus 100 times 10 to the third. Make sure you put that in parentheses on the bottom. Okay. It's not just 100. It's not just 6.38. You got to add the two. So 6.67 times e to the negative 11 times 5.97 e to the 24 divide 6.38 E6 plus 100 E3 . Anybody else get that number? 78,300 or 78,000. That's wrong. 7,839. 7,900.
Yay, I got the same number.
Got the same number. Wonderful. Any questions? Any questions?